Hello everyone, I'm back again. This is Randall Pike. I'm going to be lecturing on section 4.3 this time, bases and dimensions. So remember we're in the realm of abstract vector spaces. So a lot of the topics we'll be discussing were already previously discussed in the context of R2, R3, or Rn in general. So you'll hear a lot of the similar jargons and definitions, but in a more abstract setting here. So these are the list of topics that we'll discuss in this lecture. We'll talk about span, as you heard before, linear independence, and the bases for subspaces and vector spaces. So just to recall what these definitions are in the context of our situation of abstract vector space, usually denoted by V here. The span is the set of all linear combinations of a set of vectors, okay? So span is referring to a set of vectors, a finite set of vectors, and this term right here, span, with brackets v1 to vs, denotes this set up here, this set of infinitely many vectors. Vectors of the form x, which look like this linear combination of v1 up to vs. The coefficients t's are real numbers, t1 to ts. Okay, so that's the span of a set of vectors. We've seen that before. We've also seen this next definition, linear independence. And that's also about refers to a set of vectors, a finite set of vectors. There they are. We say that a finite set of vectors, this set of vectors is linearly independent if, whenever you write this linear combination and it equals the zero vector, then all the c's must be zero. That is, there's only a unique solution to this vector equation, and that solution is all the c's are zero. That's linear independence. And if that fails, that is, they're not all zero, so at least one of them is non-zero, then we call that linear dependent. Okay, so linear independent, all the c's are zero. That's the only solution. Linear dependent if there's a solution where at least one of the c's are not zero, is not zero. And then a basis. So a basis is a set of vectors. Okay, there it is, a finite set of vectors in a vector space. A basis for V if two things, as we've seen before, the span is equal to V and it's linearly independent. Okay, so it's the same definition that we saw in the context of R2 and R3. Actually, all these definitions are the same as we've seen before. Okay, so that's what we're talking about in this section here. So this unique representation theorem is telling us, one of the reasons why linear independence is so important to us. Okay, remember in our course so far, we've often represented vectors as linear combinations of other vectors, and we'll continue to do so even in this more abstract setting of vector spaces. So it will be important and convenient for us when we have a set of vectors that we're using to express other vectors as linear combinations of, it'd be convenient if there's only one way to express vectors as a linear combination of these vectors. And that will be precisely when that set of vectors is linearly independent. Okay, so this is a theorem. Let's read it carefully. So we're talking about a set that spans the vector space. Okay, so spanning set. Okay, so this means that the span, so spanning set is short for this. So span of this set B is the vector space. All right, which means that you can represent any vector in the vector space as a linear combination of these vectors in B. Okay, that's what spanning set means, spanning set for vector space V. Now, here's the statement, the next sentence. Every vector in V can be expressed in a unique way as a linear combination of vectors if and only if the set B is linearly independent. Okay, so we get a unique way to represent vectors only if the set is linearly independent. Okay, so that's a very important property that we want from a set of vectors that we're going to use to represent arbitrary vectors as linear combinations. So why is this true? And I think we've hinted at this before, at least I have before. Now let's take a look at the logic of this statement first. It's an if and only if. Okay, so there it is right here. Right here, okay. Now this is sometimes written as IFF, okay. And IFF, if and only if, means these two implications, this one and this one, okay. And this is sometimes written as this double arrow like that, okay. So that's just some jargon that we use in mathematics. So it's an if and only if statement. So it's a double-sided implication. So these arrows right here are if-then statements, and if and only if means the if-then implication works in both directions. Okay, so we have two things to prove when you see a theorem like this. You have to prove both implications one by one. And let's do that. So let's do the longer one, which is the if statement. So I'll remind you what the if statement is. In this case, it means if the set B is linearly independent, then each vector can be written uniquely as a linear combination of those vectors. Okay, so let me just write it out here. So the if statement is if B linearly independent, then W, so you pick a W that's a linear combination of these vectors. So let's write it with coefficients C's, okay? So C1, V1 plus dot, dot, dot plus CS, VS. So there's a vector W in the vector space V written as a linear combination of these V's. So this W, it can be written this way uniquely. Okay, in other words, there's only one set of C's which make this W. You can't do it any other way. So W has one representation as a linear combination of V1 to Vs. So that's the if statement. Okay, that's one direction of the implication. So how do we prove an if statement? Okay, so the if statement says if A is satisfied, then B must follow. So if we're trying to prove that, we assume A is satisfied, and we try to show why B must be true. So in this case, the hypothesis is B is linearly independent. Okay, so we suppose, we can assume this set B is linearly independent. Okay. Now we move to the conclusion to see if we can show that it's true. Now the conclusion's about this vector W, which is an arbitrary vector written as a linear combination of the V1 to Vs. We have to show that the C's in that linear combination for that W are unique. All right. So we pick one of these vectors, W be C1 V1 plus up to CS Vs. So here's a W that's a linear combination of these V's. We have to show that the C's are unique. All right. So now we're going to do this proof by contradiction. So proof by contradiction works when you have a statement that's either true or false. So if a statement is either true or false and you don't know which at the point now, if you can show that it's not one of them, then it must be the other. Okay, so we can prove that the statement's true here if we can show that the negation of it cannot be true. Okay, so the statement we're trying to prove that is true is that the C's are unique. So let's assume that the C's are not unique and see what happens. Can that be possible? All right, so by contradiction, so proof by contradiction, which means I assume the conclusion is false. So suppose there is another way to write this combination for W. Another way to write W as a linear combination of these ones, these V's. Okay, so that's the negation of it. Okay, so let's say that W is equal to, let's use some other letters. So let's call them T's. So T1, V1 up to TS, VS. Okay, so there's another way to write W. What does that imply? Okay, so then we have 0 vector is equal to W minus W, of course. So let's write W in one form, in this first one. And now let's write it in the second form, which is T1, V1 plus etc. TS, VS, and that's an S up there. Let me change that. That's an S there. Okay. So I have, on the left, I have the 0 vector, and on the right, I have combinations of the V1 to Vs. So let's simplify that. So I'm going to group together the vectors and put the two coefficients together. So I'm going to get a C1 minus a T1 times V1, okay? And then I'll just write it out for the second vector, V2. We'd have a C2 minus T2, V2. Plus, and then I get all the way down to the last vector, which is the S vector. I'd have CS minus TS times VS. Okay, so now look what you have. You have a linear combination of the V's, right? So there they are. That's equal to 0 vector. Now, by hypotheses, right? B is linearly independent. So by hypotheses, we must have that these coefficients are all 0. So C1 minus T1 is 0. C2 minus T2 is 0, all the way to the end. CS minus TS is 0. Okay, that's because we're assuming the V's are linearly independent. The set B is linearly independent. Well, then we see this means that C1 is T1 is equal to T1, C2 is equal to T2, etc. So there's no way you can get another a different linear combination to equal the W. Okay, so anytime you write down a linear combination that's equal to W, the coefficients must be the ones that I had at the top there, C1 to CS. Okay, so we've done the proof here. The unique representation. This is going to be very important in the next section of the text where we talk about coordinates with respect to a basis. The coordinates, I'll just give you a little heads up. The coordinates will be these numbers right here. So I'll put it in blue. So the coordinates, just to get you started, coordinates of W in basis B is C1 to CS. Okay, it's those coefficients. So you can see the importance of they being unique. So every vector has a unique set of coordinates with respect to a basis. Okay, that's very important for us. So that's one direction of the proof. The other one, the only if. Okay, so the other direction. Oops, my screen has a little dead spot on it. So only if. Okay, so now we say that suppose any vector that's written as a linear combination of the V's has a unique representation. What does that say about the linear dependence of the set B? Okay, so let's suppose that any W in the span of B, which happens to be the whole vector space, has a unique representation. Okay, which means those coefficients are unique. So W equals C1 V1 up to the end, CSVS, where the C1 to CS is unique. There's only one way to do it. All right, so now we're assuming that's true. Any vector in V in this case, because the span of V is V. So any vector in V can be written uniquely in only one way as a sum of a linear combination of V1 to Vs. All right, so now how do we get out of this that the set is linearly independent? Well, we use the flexibility in the choice of W. So let W be the zero vector. Okay, so let W vector be that zero vector. Okay, then we have 0 is equal to C1 V1 plus CS VS uniquely, because it's one of those vectors in the span uniquely. But I can see already that one particular linear combination that gives me 0 is just 0 times V1 plus 0 times Vs. Okay. Therefore, the V's are linearly independent. Therefore, B is linearly independent because there's only one way to write the 0 vector as a linear combination of the V's, and that's with all the coefficients equal to 0. Okay, so that's an easier, shorter proof, independent. Okay, so there we go. So that's a very important aspect of linear independence. This property that vectors can be expressed only in one way as linear combinations, and we'll use that in the next section here when we talk about coordinates. Okay, so that's a basis. Okay, so a basis is a spanning set that is linearly independent. Here we're talking about, previously we were talking about a basis that spans V, but it can be, you can talk about a basis for any subspace. So there's many bases for vector spaces. So these are the two most commonly discussed vector spaces so far in the book, or in our lectures. Is also the polynomials that's discussed in the book. So there's for any vector space, there's many different bases. And part of the task of a person using linear algebra in applications, either in mathematics or outside of mathematics, one of the common decisions they have to make is to find a basis for a vector space or a subspace, which one to use. Here we're going to state the most commonly used bases. We call them the standard basis vectors, and you've seen them before in the context of Rn. So for Rn, the standard basis is these vectors E1 to En, where E1, I'll just write them out here. I'll write them out as row vectors. So E1 is the vector with a 1 in the first component and zeros all the way down to the end. And E2 would be the vector 0 in the first component, a 1 in the second, and then all zeros, etc. When you get to, say, some EI down there, you'll have a bunch of zeros, and then you'll have a 1 somewhere, and then a bunch of zeros after it. And now this 1 here, let me put it in yellow, the 1 you see there, so each vector has only a single 1. This is in the ith position, the ith component. All right, so that's what the subindex means. So when you get to En, the last one, that 1 is going to be way down at the end here. It's the last entry. Okay, so we've seen those before. So that's the standard basis for Rn. Okay, sometimes it's denoted B sub 0. Okay, I won't do that yet. Now for the vector space of matrices, okay, so M sub M by N. So these are matrices of size M by N, M rows, N columns with real coefficients. So these ones will be something similar to this. So these are nice bases. I should maybe point it out here in blue. Why is this a nice basis for Rn? It's because if you take a vector in Rn, okay, so let's write it out in component form. Okay, so there's the components. then it's immediately easy to see what linear combination this V is of these basis vectors. It's simply V1 times the first basis vector, etc., etc. Okay, so I just take their components as the coefficients. Okay, so that's one of the benefits of this standard basis for Rn, is that we can easily express a vector as a linear combination of these basis vectors. And if you think back to the section when we talked about the standard matrix of a linear transformation, we use this fact there to establish the formula for the standard matrix. Remember, the standard matrix was the matrix whose columns were TE1, TE2, etc. Right? That we use this property that we can express a vector in Rn easily using the standard basis. Okay, so there's uses for this. Now, there's a similarly nice and easy basis to work with for the matrices. Okay, so m by n matrices. So I'm going to write it out abstractly here, because the matrices have a lot of entries in them. So the standard bases here will be similar things. So they're going to be matrices that have all zeros except a single one in them. And we move that one around through the entries until we exhaust all the positions. Just like we did for E1 to En. We took a vector that's all zeros except for one spot which has a single one, and we move that one across all the possible positions. So we're going to do the same thing for the matrices. So I'm going to denote them because I'm not going to draw them all out. So I'm going to list them. So there's my A11. So these are matrices. So let me just write a few down. A1, 2. Okay, so there's a whole bunch here, and I'll just write another one. So we're down the middle there. Okay, and then we'll end up at A, M, N. Okay, so there's M, N vectors here, or I guess I can call them vectors, right? Because it's a vector space, but I'll call them matrices because that's what they look like. Okay, so there's M times N matrices. Okay, I just went through all the entries that you can find in a matrix. Now let me define what these matrices are. So this is not denoting an entry in a matrix. Okay, I'm going to tell you what it is. So Aij is the m by n matrix. Remember, the basis vectors for a vector space must be of the same kind of vectors that your vector space is. So here we're talking about the vector space of m by n matrices, right? So my basis vectors are actually m by n matrices. So here they are. So the Aij is a m by n matrix with ijth entry equal to 1 and all other entries equal to 0. So I'll write out some. Okay, so I'll do example for the 2 by 2 case. So M 2 by 2, okay. The standard bases for the vector space of 2 by 2 matrices are, so let's go through it. So A11 would be the matrix, the 2 by 2 matrix with a 1 in the 1, 1 component and zeros everywhere else. So there it is. And then I'll go to A12, which will be the 2 by 2 matrix with a 1 in the 1, 2 component. So there's 1, 2 component over there, zeros everywhere else. And then I'd have A21 now moving down. So that would be the matrix with a 1 in the 2, 1 entry, which is there. And then the last one, the MN1, would be A22, which is the matrix with a 1 in the 2, 2 position and zeros everywhere else. So there you go, the standard bases. Okay, so if you take a matrix from that vector space, and I'll take an example, a concrete example, like this one. Okay, I can easily express this M as a linear combination of the basis vectors. So let's do it. So you can see what coefficients you need to pick. The first one, so this is my, let me write it out here, M1. I should do that in blue maybe. So let me write it out in blue, right? M1, M2, M3, M4. So there's my four matrices in the bases. And now I'm going to express this matrix M as a linear combination of those ones. So I can see that the coefficient from the M1 must be 1, so it's just M1. Now for M2, because I need to get that minus 2 in the 1, 2 component of my M, I must take minus 2 times M2, right? Now when I move to M3, I can see that I need to get a 3 in the 2, 1 component, so that's going to be 3 times M3. And then for M4, I'll need 4 times M4. Okay, so it's just as simple as the case of vectors in Rn. When we try to locate the coefficients up here, I just take the components of the vector, and down here, I just take the entries in the matrix I see. Okay, so it's very easy to do. When it's not a standard basis, then it looks a little bit different, and we'll see one a little bit later. So I'll just put it parenthetically here. See item 12 below for another basis of M22, for another basis. And we can represent matrices in this other basis, okay, for another basis of M2 by 2. Okay. All right, so let's move on. Good. Yeah, so here's an example. We should preface this with the comment that there are many bases. Many. When I say many, I mean different bases for a vector space. Okay. Actually, there's infinitely many. So, and they all have the property that they span the vector space and they're linearly independent, which means we can represent any vector in the vector space capital V as a linear combination, and it's uniquely as a linear combination. All right, so here's two examples. So I'm going to write out here our standard bases here. Maybe I'll just write it out in component form because that's what the other basis is. So there's my standard basis of R3. We've seen that before. And now we have this other basis. They're proposing this is another basis. So we should check that it's a basis. Okay, so here's my 3 vectors. And then 0, 1, 1. Okay. So let's check, is this a basis? Okay. So you check it's linearly independent. So is it linearly independent? Okay, that's our first question. So let's call these ones, they were calling them B1, right? So that's my B1, my B2, and my B3. Okay, so we form this linear combination of my C's and B's, the C's being scalars, the B's being vectors, equals 0. Now that's a vector equation. So in component form, you know, you're going to get a system that looks like this. So the columns are going to be the vectors B. All right, so there's my coefficient matrix of that homogeneous system I get when I look at the components of that vector equation. And then I'll need to row reduce this to see what the solutions are. And it's row reduced to the identity matrix. You can check. And so that means there's a unique solution of the C's. C1 equals C2 equals C3 equals 0. So B1 is linearly independent. Okay. Independent. Okay. Now, Good. So I can represent any vector as a linear combination of this. So if v equals v1, v2, v3, so here's my vector in R3. So I'm now doing the span question. So pick a vector there. Can we write v as a linear combination of these b's? Okay. So the system you get when you write out the components of this vector equation is going to be similar matrix. Now I'm going to write the augmented matrix. Okay, so the augmented matrix is going to be this. And then you have the V1, V2, V3. Okay. Does this system have a solution? And well, we do the row reduction and we'll get the same row reduced coefficient matrix, which is this one here. And then we're going to get things here. I don't know what they are, but they're going to be some numbers that depend on the V's. And so there is the unique solution. And actually, I shouldn't put those asterisks there. I should just put down what the answer is going to be. So it started with V1, V2, V3, but it's going to end up to be the C's, right? There's the answers, whatever they are. They're going to be functions of the V1, V2, V3. So there's the unique solution. So no matter what V I start with, because my coefficient matrix is reduced to the identity, I can express the V as a linear combination of the B's. Okay, so that establishes that B1 is a basis. So let's do it in a concrete case for V. That's what they're asking us for. So V is 1, 2, 3. Okay, so in the bases, the standard bases, okay, like I said, it's easy to pick it out. So it's going to be E1 plus 2E2 plus 3E3. And now I'll introduce you to some of the terminology of our next section. These coefficients we call the coordinates of the vector v. So it's written this way. So box v sub what you're calling your bases, coordinates of v. Okay, we'll see that in the next section. But they're the coefficients you get when you express the vector in that basis. Okay, so that's the expression in the standard basis. Now for express v in B1, in basis B1. All right, so like I said above, we have this system of equations now, which looks like this: 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, right? And then on the right-hand side, I have 1, 2, and 3. Okay, so now you can check that when you row reduce this to the identity, the coefficient part, you get on the right-hand side, the C1, C2, C3 in this case turn out to be that, which means that C1 is 0, C2 is 1, and C2 is 1, and C3 is 2. So V is equal to 0 times the B1, so there's no B1, 1 times the B2, and 2 times the B3. Okay, and you can check that out. B2 plus 2B3, so B2 plus 2B3 does give you 1, 2, 3. Okay, so you can check. All right. And so we write in this case that the coordinates of V in this other basis is this 3 tuple, 0, 1, 2. Okay, jargon for the next chapter, the next section. Okay, so that's the kind of work we need to do. We'll be doing in the immediate future, is expressing vectors in different bases. And to do that, we're going to have to solve systems of equations, just like I'm doing here. All right. So this is coordinates. I should maybe make a note here, coordinates of V. So this is going to be in the next section. 4.4. All right, we're going to talk about that. Okay, so let's continue talking about bases and dimension. So another example. So we have the dimension is the number of basis vectors. Okay, so we need to find when we want to find the dimension of a vector space or a subspace. Remember, dimension, I'll remind you here, of subspace. Remember, a subspace could be the whole vector space, so I'll just use W. The dimension of subspace W is number of vectors, and we'll see this down below, established in the theorem, is number of vectors in any basis, because the bases will all have the same number of vectors. So it's number of vectors in bases, and hence all bases. So that's this theorem you'll see below, and hence all bases. So any bases you come up with, although there's many bases, they all have the same number of vectors. Okay, that's the dimension. So if you're asked to establish the dimension of a subspace, you have to find a basis. Okay. Now this sentence here, this is not spaced, it's spanned. Okay, so here we're defining a subspace by the span of a set of vectors. Okay, so this is a subspace in what kind of vector spaces is this? It's M22, subspace in the vector space of 2 by 2 matrices. Okay, because they're 2 by 2 matrices. So let's call this set S. Okay, so I have a set of vectors from the vector space M22, 2 by 2, 4 vectors. Okay, so the span, so W, the subspace is this W, so W is the span of S. And our question is, what is the dimension of S? So from above, we've seen already from above, just as I mentioned it here, the dimension of M to M by N actually is M times N. Okay, that's from above because I'm referring to this up here. This one right here, standard bases for M n by N, the M by N matrices, and you'll see there's M times N matrices there, right? That's the set of vectors in that vector space that span the whole vector space, and we'll see they're linearly. You can see they're linearly independent. It's easy to see. So I should say this here. So check that. It's easy to see that B is linearly independent. So we did this kind of discussion about linear combinations and linear independence of matrices in the previous section in chapter 3. Is linearly independent. It's easy to see it in these vectors. Just as it's easy to see that the standard vectors in Rn, the E1 to En, are linearly independent. Okay, so so there you go. You have M times N vectors spanning the vector space M sub M by N matrices, and they're linearly independent. So the dimension is M times N. We know that. So that's the dimension of M2 by 2. So the M2 by 2 has dimension 4. Okay, I say this because our W is firstly, it's a subset of M2 by 2, so it can't have a larger dimension. So its dimension is 4 or less. So we know that much. But is it 4 or is it less? If it was 4, then this set S would be a basis for M2 by 2. It would be a basis. So we're not sure if it is or isn't. We need to check linear independence. So I'm going to do that now. Okay, so let's check. Determine if if set S is linearly independent. Okay. Now that's the same definition that we've seen before for vectors, except with the elements, the vectors in quotation marks, are these matrices. So I have to look at a linear combination of these matrices. So let's call it M1, M2. So these are the matrices in that set S. So I have this linear combination. Equals 0. Okay, now notice this is an equation of these elements in this vector space. So the m's and the 0 on the right is our 2 by 2 matrices. So that's an equation, a vector equation. So in components, okay, I have this equality here of matrices. So 2 by 2 matrices on the left and the 0 2 by 2 matrix on the right. So two matrices are equal if you go back to that chapter, if and only if all the entries are the same. So we go through the entries, and I should call it entries maybe. Okay, let me just call it entries. All right. So I see that this matrix here, let's write it out. Okay. So let's just do this sum. So look at the set S above there. So what is the 1, 1 entry in this sum on the left? Well, it's going to be T1 coming from M1. There's no T2 because there's a 0 in the 1, 1 entry in M2. There's going to be a T3, and there's going to be 2 T4 in the. So that's the 1, 1 entry of the matrix on the left. Okay, because I've added up this combination T1 M1, T2 M2, T3 M3, T4 M4. Remember, when you multiply a matrix by a scalar T, you're multiplying every entry in the matrix by T. So what's the 1, 2 entry? So first column, second entry. Well, I go up there, T1 times N1. Its 1, 2 entry is minus T1. Okay, and I go over to M2, I see that there's a 3 there, so T2 times N2 has a 3 times T2 in the 1, 2 entry, so 3 times T2, and then a 2 for M3, so 2 times T3, and finally a 4, so plus 4 T4. Okay, so that's the 1, 2 entry. So there's the first column of my matrix on the left. That's the first column. And then I go to the second column. So what's the 2, 1 entry, or 1, 2 entry? So going back to my 2, 1 entries in my set S up there, I see I get a T1 coming from the M1. I get a T2 coming from the M2. I get a minus T3 coming from the M3. And I get a T4 coming from the M4. Okay. Now the 2, 2 entry of the sum on the left is coming from the 2, 2 entries of each of the matrices in S. And looking through that, I see a T1 for M1, a minus T2 coming from M2, a minus T3 coming from M3, and a minus 3 T4 coming from M4. All right, so there's my 2 by 2 matrix on the left. And this is equal to, so now I can write out the matrix on the right there, 1, 2, 3, 4. There's the 4 entries. Okay, so now you see why I get 4 equations now. So I get T1 plus T3 plus 2T4 is equal to 0. And let me write it in this order. So I'll go to the next, I'll go to the 1, 2 entry. So it's going to be T1 plus T2. It doesn't matter how you order the equations, but I'll order them this way. 0, and then I'll go to the 1, 2 entry, which is this, plus 3T2 plus 2T3 plus 4T4. Okay, that's 0. And then finally the 2, 2 entry, which is T1 minus T2 minus 3T3 minus 3T4. That's equal to 0. Okay, so my unknowns are the T's. So let's write out the coefficient matrix. This is a homogeneous system, so to solve it, I just have to look at the coefficient matrix. So in my T1 column, I see a 1, 1, minus 1, 1. In my T2 column, I see a 0 at the top, and I see a 1, a 3, and a minus 1. In my T3 column, I see a 1 in the top, a minus 1, a 2, and then a minus 3. And in the T4 column, I see a 2, a 1, a 4, and a minus 3. So that's the coefficient matrix of my system there. And you can row reduce that, you guys check, to 3 leading ones. So here they are, 0, 0, 1, 0. And then I get my last column is this. Okay, so that's the reduced row echelon form. So what this tells me, if you notice, there's the 3 leading ones. Okay, so what we've accomplished is the following. First of all, we see that this last column here, that's the T4 column. This tells us that M4 is this particular linear combination of the previous 3. It's actually the sum of them, M1 plus M2 plus M3. Okay, so that comes from this row reduction, and you can check yourself, right, that M4 is the sum of the previous 3. Okay, you don't need to do this by inspection. You know, setting up a system of equations like this will do it for you. Okay, so the set is linearly dependent, but because there's 3 leading ones there, those columns, the T1, T2, 3, corresponding to the M1, M2, M3, those are linearly independent vectors. So a basis for what I'm calling W there, which is the span of that set, is just M1, M2, M3. And so the dimension of W is 3. Okay. Okay. So to determine the dimension, I needed to find a basis. And to do that, because the subspace S was, so it's not the subspace, W is the subspace, it's the span of S. It was given as the span of a set of vectors. You could work directly with that set of vectors to determine a linearly independent set. Okay. I want to do at this point another one that's related to this problem here. Okay, so this is something that's in the book too, but I think it's good to take a look at this. It's something that's a little bit more abstract. So I'm going to call this 7b as a reference. Okay, so the set here now is also going to be a subset of vectors of matrices, 2 by 2 matrices. So they're of this form: A, B, C, D. Okay, so there it is, such that A plus B equals D. Okay, so this is a subset of the 2 by 2 matrices. So the question here is S a subspace? How's that? Back to the beginning. And if so, find a basis and hence the dimension of it. Okay, so it is a subspace. So let's do that. So it's closed under addition. Okay, let's check that. Okay, let's check that it's closed under addition. So I'm going to take M1 and M2 from the set S. Okay, so let's give me more space here. So I take 2 matrices from the set S. Okay, so I'm going to call them A1 with subscripts 1, so A1, B1, C1, D1. And my M2 is going to be A2, B2, C2, D2. Okay, so I've taken 2 matrices from the set S. Now notice that I'll just write it here because we're going to use it later. So A1 plus B1 is equal to D1. Okay, and A2 plus B2 is equal to D2 because they're from S. So now I add them, M1 plus M2. Okay, so let's add them. And when you add matrices, you add components. So A1 plus A2 is my 1 entry, and then I get C1 plus C2, 1 2 entry, and then 2 1 entry is going to be B1 plus B2, and 2 2 entry is going to be D1 plus D2. All right. So that's the sum. Now let's write this as A tilde, C tilde, B tilde, D tilde. Okay. And now we check that, is this M1 plus M2 in the set S? Yes, it is, because you can check that the A tilde plus the B tilde equals the D tilde. So it is in S, okay? Because A tilde was A1 plus A2, B tilde was B1 plus B2, and that does equal D1 plus D2 because of these two, okay? So, and now you take a K times M1, say, okay, and that's going to be KA1, KB1, KC1, KD1. So I multiply it by scalar, and you can check that for this one, let's just call it bars this time, A bar, B bar, C bar, D bar is in NS because, once again, A bar plus B bar equals D bar. Okay, so it is a subspace. Okay, so now we can talk about the dimension. You can't talk about the dimension of a subset of vectors, but you can talk about the dimension only of a subspace. So it is a subspace. So we're trying to find the dimension of this subspace. Okay, so in other words, we're trying to find a set of vectors that span it. Okay, now, so that's the basis question. Now let's be creative here. So a basis of this, eh? So notice our condition is, and I'll just write it down again here, A, B, C, D with A plus B equals D. So we have to think about how I can express a vector or a matrix like this with this property. So I claim that because if you look at it, the D contains an A in it. Okay, so I'm going to write down. I'm going to try my best to mimic the standard bases for M2 by 2, which is those matrices with a single 1 in it. Okay, so let's try to go in that direction. So let's start with that 1 1 entry being a 1. Okay, now remember, I'm going to use this matrix as a basis, so it's going to create it's linear combination. I'm going to use this matrix as in the linear combination to create these matrices that look like this. So I'm going to multiply this matrix by the A, right? Because there's the 1 there. But my D must contain that A, so I have to put a 1 there. Okay, so I can't use the first standard matrix that I had above, 1 0 0 0, because when I multiply that by scalar, I'm not adjusting the 2 2 entry equivalently, okay, which I need to in this case because D contains that. So now that's a good strategy. Now when you get to B, the same sort of thing happens. So my B is in that entry, the 1 2 entry. So when I multiply this matrix by some scalar, I'll get a scalar in the 1 2 entry, but that scalar must also appear in the 2 2 entry. So that's why I need a 1 here. You see that? Okay. Now, so that takes care of my A's and B's and D's, doesn't it? So now for the C, notice C can be anything. There's no condition on my C. So I'll use this matrix for that. Okay, so I claim that this is a basis. This is a basis for the set uh, S. Okay, yeah. So S is a subspace, right? So this is a basis for S, and so the dimension of S, the subspace S, is 3. Okay, so that's a basis for it. All right, so that was another example using matrices. So the basis reduction theorem. Okay, Good. So you have a set of vectors that spans the vector space. Okay. So there's B, spanning set. So that means that the span of B is equal to V. That's what spanning set means. Okay. So span of B is equal to V. Um, then some subset is a basis. Okay. So the fact that it spans V is one thing. That's one property of a basis, but it doesn't have to be linearly independent. Okay, so it's just spanning the vector space. So I can write every vector as a linear combination of these V1 to Vs. Okay, now we want to, so that the theorem is telling us that some subset of this set of vectors is a basis. Okay, so maybe not the whole thing. It could be the whole thing, doesn't have to be the whole thing. So that's the theorem. Let's get an idea of how this works or why this is true. And this is a very practical strategy because as we've seen above and in other examples in this course, one of our most common ways to specify a subspace, which could be the vector space itself, is as the span of a set of vectors. But we'd like to have a basis for it. So that's a start of obtaining a basis because you have a set that's spanning the subspace you're interested in. You just have to determine linear independence, and it may not be linearly independent. So what we're doing here is we're going to, in the case where it's not linearly independent, that is, it's linearly dependent, in that case, we're going to remove vectors until it becomes linearly independent. Okay? So we work step by step here. Okay? So if B is linearly independent, okay, there's nothing in the statement talking about its linear dependence or independence. So if B is linearly independent, I want to start with that one. Okay, independent. Then B is a basis. Okay, then we're done. We don't have to do any work for V. So that's in a concrete example, you could check to see whether it's linearly independent or not. All right. But if not, if B is linearly dependent, then I'm going to remove a vector. Okay, and which one do I remove? Well, you can't just remove any vector. You have to remove an appropriate vector. Okay, so if it's linearly dependent, and this will tell us which vector to remove, then because of the definition of linear dependence, which means that then there's a linear combination of these vectors that adds up to 0. Okay, so let me write out a linear combination. T1 V1 plus TS VS VS, and it adds up to 0. 0 vector, okay. I'm not putting my arrows over here, but you can tell which ones are vectors, which ones are scalars. So there is a linear combination that equals 0, but not all Ti equal to 0, right? Because it's linearly dependent, right? That's the hypothesis. Okay, so this must be true then. Okay, so what we do is we pick that one. Okay, so suppose, well, let's just call it tk is not 0. Okay, there could be several of the t's not equal to 0. I'll just pick one of them. So tk is somewhere between t1 and ts, or including t1 and ts. So if tk is not equal to 0, then we can remove, and I'll justify this, vk. Okay, so where the tk is not 0, it's attached to a vk. This vk can be removed. Okay, we can remove VK from B, the set B, without changing the span. Okay, so call this new set B1. And the span of this new set, which has one less vector, B1 has one less vector than B, and the span of B1 is equal to the span of B. You haven't changed the span. Okay, if you remove a linearly dependent one, you can see that. So this is discussed in the book. It takes some time, but I won't do it here. I did do it in one of my lectures before in a concrete case, so you can see what exactly why that's true. So go to my lecture. That was 2.3, item 4 in the notes, and the time is about 56 minutes. Okay, so I did pick out one of these vectors, and I showed you that it did not alter the span of the whole set. Okay, so that's the idea. So now you have this smaller set B1. Okay, you started with the set of vectors B that was dependent, and you have B1 now. So now you ask again, if B1 is linearly independent, then that's a basis. Okay, so you check again, and you know how to check linear dependence or not. If it is linearly independent, then B1 is a basis for V. But if B1 is dependent, linearly dependent, then you do the same thing. Okay. Then remove a vector. Okay, and you can't just remove any vector. It's got to be one that is associated with a non-zero coefficient. Okay, so but that one you can remove. And there may be several of them, but you just remove one. So if B1 is linearly dependent, then remove a vector to obtain smaller set B2, and then you just keep going until you have a linearly independent set. Okay, etc. until you reach a linearly independent set. Okay, so that's the way you do it. Independent set. All right. Okay, so that proves this theorem. Okay, and the enabling operation is which vector to remove from that set, and it's the vector associated to a non-zero coefficient in this equation here when you write out this equation for your set of vectors. Okay, good. So that's how you do in practice. You do often get a basis for a vector space or a subspace. It's first defined as the span of a set of vectors. You check then to see if that set of vectors is independent or not. If it is, that's a basis. If it isn't, then you simply start to remove vectors until you've reached a linearly independent set. Okay. Moving right along. So the dimension theorem. Okay. So what this is telling us is that although there's many different bases for a vector space, they all have the same number of vectors. So S equals K, and that's why we define the vector space to be the number of basis vectors. It's independent of the actual bases. Okay, so the basis vectors can look quite different, but there's always the same number of vectors. So there's one set of vectors with S and one set of vectors with K. All right, so in words, so although there are many bases for a vector space or subspace, they all have the same number of vectors. I'm just rephrasing this theorem here, same number of vectors. And that's why we've been using this theorem already before we stated it. That's why this definition of dimension, being the number of vectors in a basis, is well defined. It doesn't matter what basis you pick, and you're getting to realize now that there's many bases for subspaces and vector spaces. But the fact is that the number of vectors will remain the same. Okay. So this is the proof of this. So this is proven in the book. So proof uses this theorem that's not mentioned here. So theorem, I'll write it out here, 4.3.3, which states that if the dimension of V is n, okay, so there's a basis with n vectors in it, then any set of vectors from V, any set of k vectors from V where k is bigger than n, okay, is linearly dependent. Okay. Good. So that's that. What do we need to do next? Okay. Yeah, so we can do this proof now. Okay, so therefore, if we have two sets of vectors that both span the set V. Okay, so I'm going to alternately consider one of them as being a basis, and then see what the consequences is for the other set of vectors. So let's considering V1 to Vs to be a basis for V, okay, considering that to be a basis for V, then then according to this theorem 4.3.3, okay, we must have that K, that's a K, yeah, K is less than or equal to S, okay? Because if K was bigger than S, then it would be linearly dependent, and we're assuming that these are both bases of the vector space. Okay, and then I look at it in a different way now. So similarly, considering the other set as a basis, so this set here, U1 to UK as a basis for V, then by this theorem, we must have that S is less than or equal to K. Okay, so there's two conditions on these numbers. And the only way this can be resolved is that they're the same. S is equal to K. All right. So any set of bases any bases you get for a vector space or a subspace will necessarily have the same number of vectors. So that's why this definition of the dimension of a vector space or subspace being the number of vectors in any basis makes sense, because it doesn't change if you change a basis. Good. Now, basis extension theorem. Okay. So this is a method to create a basis for the entire vector space, starting with some linearly independent set. Okay, so you have a vector space. It's n-dimensional. Okay, so you have k vectors, and k is less than n. You have some vectors, could be one vector. I mean, in practice, sometimes it's just a single vector. You start with one, and you add vectors to it to create a basis. Right. So starting with k linearly independent vectors, so notice it's linearly independent. You can find the remaining number to augment those initial vectors so that your complete set of vectors is a basis. Okay, so you have to add the you need to add the n minus k vectors to the initial set. Okay, somehow. All right. Now, I'll just say it abstractly like they do in the book here, but there are very concrete ways to go about this, and I'll mention that down here. So how do we do this? Why is this true? Why can we always extend a set of linearly independent vectors to a basis? Okay. Well, the idea is the following. So so first of all, since k is less than n, there is a vector that's not in the span. So there's a vector w, let's call it, so this will be your next vector to pick. So wk plus 1, so that's the next vector to pick. You notice in the list here, that's the next one. Okay, so how do I get that next vector after the vk? Well, it's any vector, so in your vector space v, that's not in the span. Okay, not in the span of B. All right. So because your V is n dimensional and k is less than n, the span of B is not V. Otherwise, V would have dimension k, right? But it doesn't. It has dimension n. So there, it doesn't span V. The span of B is not all of V. So there's got to be something outside the span. And pick any vector outside the span, wk plus 1. Call it wk plus 1. Then now here's the good part here you have to think about. V1 to V2 up to Vk, and now you add this vector to that set is linearly independent. Okay, so notice we started with linearly independent vectors V1 to Vk. I added another vector. Okay, now generally that might ruin the linear independence, but not in this case, not if your vector you add is from outside the span is linearly independent. Okay. All right. So, I mean, that should be pretty clear to you. It can't be linearly dependent, right? Remember, linearly dependent means one of the vectors is a linear combination of the others. Well, this wk plus 1 is definitely not a linear combination of the others because it's not in the span of the others. So it's definitely not the culprit. But the V1 to Vk, those other ones, they're already established to be linearly independent. So none of them can ruin the linear independence. So it should be pretty obvious that this new set, which is one bigger, is linearly independent. All right. And now you just keep going in this way. Okay, so we added one vector. If that equals n, then this set is a basis. We've already reached it. Okay. But if it's not, okay, there's k plus 1. But if k plus 1 is not n, that's a basis for V. Otherwise, okay, so otherwise means that k plus 1 is still not big enough. We find the next vector, which will be some vector, let's call it this, not in the span of these guys. All right, so not in the span of the ones I have so far. Okay, and continue until you get n vectors. Okay, you get n vectors. So the initial vectors, the v's, we call them, plus these w's that you keep adding on whenever you're not, the set does not span the whole vector space. Okay, so some point it will. Okay, and that will be when The number you've added on gives you a set of n vectors. All the ones you've added on, the w's, in addition to the v's, gives you n vectors. Okay. Now, there is a concrete application of this in the previous section of the book. So let me just point it out here. So that's theorem 3.4.10 on page 202 of the text for a concrete way. This is abstract what I just did, but there's a very concrete way to do this using matrices. So that's in the context of Rn to do this for the case the V is Rn using matrices. Okay. It might not, it's not obvious to you at this point now, but every vector space is like an Rn actually. Okay, so that's why if we can do these calculations in Rn, then we can do them in any vector space. That's something to be seen later. Okay, so there is a concrete way to do this using the row space. Just to give you a hint, row space of a matrix and the null space of a matrix. Okay, so those calculations, if you go back to that theorem, you'll see they're using the vectors in the rows and the vectors in the null space to extend a set of linearly independent vectors to a basis. Okay, so that's a very practical way to implement this. This looks very abstract, but it can be done very practically. All right, so some examples. Well, here's an example here. I'll draw a picture of this. We can see why this is going to work. So here's my coordinate axes, so in R3, and I'll try to draw a plane. All right, so there's a plane, kind of an oblique plane. Notice the plane is going through the origin, though. Okay, so you have to imagine that because it's a subspace, right? So there it is. So I want to use this plane to get a basis for R3. All right, so now there's a so there's a set of vectors. Remember this plane, you know, if I do it, that's the scalar equation of this plane, but the vector equation of this plane, I'll write it out here. The vector equation looks like this. This is how we've been denoting it, right? So x is equal to t1 v1. So now I'll just indicate the vectors here. And there's no constant vector because it goes through the origin. So you want those two vectors or any two. So here's a v1, say, and there's a v2. Okay, so if you can imagine those two vectors in the plane, right? So the span of those vectors is this whole plane. What I should pick then is this normal vector. So here's a normal vector. So that n, okay, not only is it not in the plane, it's orthogonal to the plane, but actually any vector that's not in this plane will work. But I'm going to take the normal vector, all right? And that would be my three vectors for the bases. So I'm just going to write it out here. The answer, bases, is going to be my v1, my v2, and my normal vector. Okay, because the v1 and v2, I'll pick v1 and v2 first, and that's not hard to do. And then the n is also not hard to do because I can see it here. But it's clear that the n is not a linear combination of v1, v2. So this n here is playing this role of the wk plus 1, right? I pick a vector that's not in the span. So this n is not in the span of v1, v2 because it's not in the plane. But you don't have to pick the normal. You can pick any vector that's not in the plane. And you add it to the set v1, v2, then that set of three vectors will be linearly independent. Okay, so I'm implementing this abstract approach above here. So how do I get the v1 and v2? Well, you simply pick, because this plane is going through the origin, you simply have to pick 2 points that sit on this plane. So looking at the scalar equation for the plane, I can pick, for example, 1, 1, 1. I can see that v1 is in the plane, right? Because it satisfies the equation, its components. And v2, I can take another one. Okay, there's many choices. Okay, and then for the n, now n just has to be any vector not in the plane. okay? But I'll take the normal because I know for sure it's not in the plane. Otherwise, you have to check that the vector is not in the plane. So there we go. So that's another basis for R3, okay? Set of three linearly independent vectors. And I want to do just one more thing here. This one here. Yeah, okay. So I think that's probably good enough because it's probably getting kind of late here. So I'll end it there, but there are many examples. And the one example I was suggesting you look at is, let me write it here. So C example. And this is one I'll do in my class lecture, okay? Kind of extending this idea in another context. So this example 4.3.1 in this section 4.3 is a discussion of a similar thing to extend a basis to starting with two matrices in R in M 2 by 2. So we have a set of two matrices. Let's just call them M1 and M2 that you can see what they are there. Extend that to a basis. Okay, so that's a good example to look at. Extend to a basis for M 2 by 2. Okay, so remember this is dimension 4. Dimension 4. So you need to add two more vectors. Add. I'm calling them vectors, but they're, I mean, concretely they're matrices here, right? But we're talking about a vector, the vector space M 2 by 2. So, you know, technically they're we call them vectors. So need to add two more basis vectors. Okay, so that example in the book, this 4.3.11 will give you a way to pick two more matrices that are not in the span. And it's a good example. It takes a little time to work out. That's why I'm not going to do it now because it's already been too long, I think, this lecture. But take a look at that for another illustration of this dimension extension theorem, basis extension theorem, which is a very important technique used in linear algebra. This one here I just did with the plane is a pretty straightforward one, very familiar to you, so it should be very believable what's going on. But you should get used to these other more abstract examples, and this example 4.311 I think is a good start to go study that one and then do some examples like this in that section of the book. I'll do some like this in my class. So I think I'm going to end it here, and I will see you in the next section 4.4.